Yeah, so you can post, yeah, so it should be fine to post for everyone.
Otherwise, we may lost the signal because, for example, the first server is posted and then CLI is working out, but it didn't have a chance to remove the server.
Yeah, so to avoid this kind of corner cases, yeah, I think it's okay to post to everyone. Yeah, it should be fine.
Okay.
Yes, so yeah, because again, it depends how exactly you implement, and if you think that your algorithm only works correctly if it posts to everyone, that should be the case, right? So then just post to everyone. But again, post to everyone who is participating in this channel, right? So not to every channel. So I think that's the global test that otherwise can fail, right? Okay. Let's see. Let me open the slides. So last time we started storage. Well, we started discussing IO and storage. Let me just open the slide just a second. Yeah. So we stopped at the Linux storage stack. So just let me show you one more time that stack. So recall how this is translates to the Linux storage stack. So you have an application, so we have application calls like write, read, and so on. That eventually gonna reach the VFS layer. So in the VFS layer, we have different file systems. For example, XT4, maybe Btrfs, XFS, I don't know, ISO file system, anything, right? Well, I think it's is it called BARFS? Yes, sometimes it's called BARFS, sometimes BARFS. I don't know why they pronounce it differently. Anyway, it's like based on B trees. Yeah, so and yeah, network file system, NFS, and so on. So that means it also can reach different kind of file systems, right? So it's not just, it has to be storage file system. It can be something that is over the network. So then we finally reach block IO level, if we are talking about something that requires block storage. So if it's NFS, it's not going to reach block IO level, it will reach NIC eventually, right? But if it's XT4, it will have to go to eventually to the block IO level, especially because, I mean, it shows the page cache. I'm pretty sure XT4 will also talk directly for something, not just for page cache, because there's certain things that you need to write to the journal. You have to write something to the superblock and so on, and that should probably bypass page cache. Yeah, so yeah, and then finally it reaches the specific block block interface such as CASI, whatever it is. So let's talk about Linux VFS. So Linux virtual file system. So what does it contain? And what is the purpose of Linux virtual file system? It's a basically common abstraction for file system. Again, virtual file system is not a real file system. It doesn't even have to do anything to do to the file system itself, but it's just basically whatever common things that you have for every file system, it basically belongs to the virtual file system. It's like you create maybe some abstract class, and then from abstract class you can reach some specific implementation, right? And that's pretty much what it is. In fact, even the idea is similar, right? So because you're going to have function pointers, which is kind of similar to what we have in C++ virtual functions, right? And you know, or in Java like interface and whatever it is, right? Yeah, so we were gonna have key data structures here in VFS. inode. So this is inode is the basically something that is roughly corresponds to every file, right? So I mean, I say roughly because you know there might be some exceptions in files, some file systems. But you know, for every file you have an inode pretty much. And by file, I mean not just a regular file. So for example, your directory is also viewed as a file, or your symbolic link or any other link, any other things. Well, hard link will not be a separate inode, but symbolic link will be also a separate inode, pretty much a separate file. So a symbolic link is basically a file which contains a path to another file. So we'll get to that. So yeah, so inode roughly corresponds to a file, and a file in a more general sense. So, and then we have file descriptors. So remember that you will, well, I should rather say, I guess, yeah, so file descriptors, but there is also so-called file descriptions, right? So file descriptor is a number that you have in user space, and that file descriptor will roughly correspond to some structure in the kernel. So it will map to the structure in the kernel, like file file structure, and that will sometimes called file description. So directory entries. So why do we need to do that? So why do we need to do that? Well, because the first thing, I mean, of course, obviously, one thing is that we need to have some common interface for everything. When I use a read or write operation, I don't care what file system it is. I just want this stuff work, right? So I just have this mount point, whatever this mount, like I have file path. I just want to access that file. I don't care what file system it is. So that's obviously one reason. And the other reason, another reason is that it provides uniform file system caching. So remember that you also need to connect to the memory subsystem, and you need to connect to the page cache. So sometimes you want to cache some files in memory. So it's something that has to be tightly integrated with the memory management system. So yeah, you have to have some uniform mechanism to access page cache and all this stuff, right? Also, another thing is, aside from page cache, we have things like when I access some files, and I access these files, you know, maybe frequently, I want to keep, like as I said, inode roughly corresponds to every file. So I want to keep every inode also kind of cached, right? So I don't want to read it from disk over and over again. So another thing is to keep inode cache, not just some data cache for the file data. Also directory entry caches, right? So when I want to traverse some path, find where the file is and so on, I want to keep that stuff, you know, ready so that if I'm opening another file in the same directory, or like maybe part of this path is already traversed, so that I can get it from the cache. Yeah, so we basically have these three things, like page cache, inode cache, directory cache. So let's talk about page cache first. So that's basically rough, as I said, cache for storage pages. So whatever, like whenever you read some data from a file, you know, you want to read it over and over again. You want to have some way to expedite this, right? So you want to have that in RAM. So that will accelerate slow storage, especially if you like with legacy devices such as hard disk, that was a big deal. But now with SSD, maybe it's less of a problem, but still SSD is slower than your RAM. So typically, or at least, well, I mean, yeah, still there is difference. Yeah, the gap is actually narrowing, and at some point we were, there was a hope that we will have this persistent memory, right? So that means you don't need storage at all. But apparently Intel abandoned this, at least Intel Optane DIMM or whatever, right? So like persistent memory is not something that is being kind of commercially available anymore, right? Um, so we in page cache we store basically things as pages. Again, this is tightly integrated with memory management subsystem, and we want to have pretty much reuse whatever unused memory we have, unallocated memory for that thing, right? So we want to just cache that stuff because it's free, memory is not used. Why not to keep some useful stuff there? Yeah, so therefore it doesn't waste memory, right? So that's the example. That's the benefit, right? So it just basically use your memory more efficiently. Doesn't affect user memory capacity. The moment you say, I need more memory, okay, we can just evict the stuff and, and that can go to disk and we can throw it away and, that shouldn't cause any issue. So yeah, so for page cache, it's both reads and writes. So it will have this write back protocol. And sometimes, sometimes I believe you want to also pin some pages in page cache, especially if let's say there is let's say you have we will probably talk a little bit about journaling file systems, but for journaling file system it may be necessary to make sure that data is not written to disk before it's written to the log area, right? So they may sometimes want to pin it and write some data there, but not put it on the disk yet. So there's that's like to support journal protocol. So there is some exceptions, right? So there's some exceptions to that, but those are typically controlled by this page cache mechanism. So periodically it will just flash it on a disk. So that means you wrote some data in cache, like it's going to be stored in cache, but periodically it will be written to the disk. So again, this is both necessary for safety because you want to make sure the data is written at some point. Because I remember I was like using some operating system which has like buggy file system, buggy operating system, and there was journaling file system. Basically, all work I did disappeared after after reboot because it didn't flash uh, any data to disk automatically, and there was some issues, right? So I got this habit to periodically kind of call sync, right, so that I at least know that it is going to be written to disk. Yeah, so yeah, that's exactly what you can do, right? So you can trigger sync, fsync. Fsync is for specific file, and sync for the entire file system. Well, sync actually will do it, I think, across all file systems because that's, there is sync call for a file system, but there is also, I think, when the sync command probably do it for everything, if I remember correctly. Okay. Yeah, but fsync for a specific file. So regarding inode cache, and regarding directory entry cache. So for inode cache, why do we need it? Well, the same deal is for not just for data, but to access some metadata. So inode basically keeps some metadata for a file. So I just want to periodically, I want to have that readily available, especially for files that I access all the time. So for directory entry cache, for file paths or parts of the file paths that I access frequently, I also want to cache that. Okay, any questions so far? Okay, Yeah, so yeah, let's look now at some IO devices and how these IO devices work, right? So far, I mean, I just gave you some introduction to virtual file system, and how we eventually reach the IO layer. But then finally, we reach this IO device, right? So how does it even work? Just to get some idea about this, right? So in IO device, basically how you can actually view any like canonical device. You fundamentally have multiple registers, like status register, command register, and maybe data register. So that kind of determines the interface, like for this device. By the way, how can we access these registers? Any ideas? Like, I mean, for CPU, I have registers, right? I can access RAX, RBX, RCX, whatever. So how can I access any like how can I access registers from my hard disk? Any guesses? So basically there are two ways, and we will discuss them. But like to keep the answer kind of short, right? So that you have at least some idea, right? Before we go into this detail. In modern systems, you can map these registers directly to memory, right? So that they will appear as a regular memory addresses. And you like for example, we had frame buffer in project 2. That's also a special type of memory. It's not really a regular RAM. It's like more like something that would directly be mapped to a pixel. So the moment you modify this memory location, it will modify color or whatever, like on the screen, right? So that's a special kind of a memory address. Okay. So and then we of course have some, we have some microcontroller, maybe memory, whatever it is, right? So like for example, I guess SSDs also have their own like DRAM there, right? So DRAM chips so that they can also make it faster. Yeah, anyway, yeah, so by the way, why do you need a microcontroller? Well, typically because you want to kind of offload your CPU, right? So you don't want to use your CPU for things that can be done locally, right? And by locally, I mean also imagine that this device is behind some interface, right? And will probably be slow to access this device otherwise from CPU. So it's better to have something that is local to that device, like maybe some inexpensive processor that is directly connected to this device and doing some stuff related to this device. And then maybe we'll get some interrupts or something like this, notifications in our system, right? So that's the idea, right? So we want to hopefully your CPU in your system, right? It's probably an expensive part, right? So you wanna do only like computationally intensive tasks there or whatever, right? I guess nowadays people watch supporters, I don't know, right? So maybe they're not doing too much computational intensive tasks, but in general, the idea is that your CPU is supposed to be busy with some important stuff, right? And and so like things like checking whether like data transfer is complete or something like this that can be offloaded to a smaller processor which is directly connected on this board, like hard disk or whatever it is, right? Yeah, so also for internal structure, uh, you know, again, as I said, we will have effectively its own local CPU or local processor, memory, other chips, right? But also we of course we're gonna have some software running there, and this software is known as firmware. Yeah, so that's also probably you have heard about this already, right? Yeah. So what kind of hardware interface do we have? Well, effectively, we have to control this device through these registers. So whenever we're going to issue some command by writing some command to the command register, check status, then retrieve data or whatever it is. So basically, 3 registers. So let's look at this canonical protocol. Again, this is not something that you will have to use in modern devices, but like what is the fundamental approach that we want to use? So first of all, we want to make sure that the device is ready. So we check the status. So while the status is busy, we are waiting, right? Okay, after this, maybe we wrote some data to the register. Then we issued some command. Maybe we want to write something to this device or whatever it is, right? And then, then we check status. While it's busy, we are waiting, then it's stopped, right? Of course, that's not how it's done for modern devices, right? So because otherwise you would waste a lot of CPU time because you are waiting while it's busier, then that's it's a really problematic, right? So this method of device interaction is known as polling, right? So you are responsible for checking whether the device completed this operation. So why is it bad? Well, it's bad because you're wasting CPU time, and hopefully CPU time can be used for something more important. Well, I don't know, or like again, maybe it's watching some photos or videos of that. Yeah. Anyway, yeah. But anyway, you would actually notice that for some on some older systems, I think there was some joke about a floppy. Yeah, so what is multitasking? And in Windows 95 or something like this, there was some joke that yeah, just please wait while I finish formatting my floppy disk. I will show what multitasking is. So basically, when you kind of access floppy disk and try to do something with this, that would kind of freeze the entire system, right? And yeah, so that was a problem. Um, so this is actually kind of related to this, right? So because that would kind of paralyze the entire system because your CPU, well, especially in the past, because we didn't even have multiple cores in the past. So it was basically the only CPU you have busy checking the status of the controller. Yeah, so okay. Yeah, so there are 2 main approaches, right, that we can use to lower all these overheads. So one of them, and they actually have to be, typically we use them both, right? So it's not just one that we use. So one is that we want to have a notification. We don't want to periodically check status. Is it complete or is it not complete? So we want to get an interrupt. So we're gonna say, okay, this hard disk has its own small processor. Let it check the status when it's ready and when it's not ready. Once it's done, just trigger an interrupt, and the CPU will wake up and and do and will know that this transfer is complete, right? So whether it's a read transfer or write transfer doesn't matter. So that's one thing. So this way we can eliminate this checking. So the other thing is direct memory access engine, right? So sometimes, because we also need to transfer some data and we want to avoid this overhead. So I will show you in a moment. So even for that, we waste CPU time. So we want to save CPU time here as well. So let's look at the interrupts first. So you read some data from a device. So basically, yeah, so you have 1 and 2 processes, right? And if you do polling, then you pretty much do polling, right? So now with interrupts, you can basically schedule another task. Yeah, this task is blocked. Task 1 is blocked, but I can switch to another task while I get an interrupt. So once I receive the interrupt, I can get back to the original task. So yeah, so basically, that will allow you to achieve better CPU utilization because now you're not wasting this time because you otherwise have to spend this just for polling. So, but sometimes polling is still efficient. So when is it efficient? I guess at the point when you have to have, when the interrupt will arrive fast enough, or maybe the interrupt has a lot of overheads and so on, right? Because interrupt is not free. Remember that we have to go to the interrupt handler, we have to save, restore registers. At least that's the side, that's the thing that we do in the OS, but there is of course also hardware overheads for that and so on, right? So there is a lot of like the cost is not negligible for interrupts. So we want to do that only after, some time. So therefore, for extremely fast devices, it's still better to use polling. So now for direct memory access. So let's say we want to write some data to the disk. So the problem is that we have to spend time now for writing it to the disk. Yes, we can schedule task 2, but before we can schedule task 2, we have to complete the data transfer, right? So, and that is a problem. So basically, instead, with DMA, what we can do, we can say, okay, I give you this access to this memory address, so the disk can go and transfer this data without using the CPU pretty much, right? Using this DMA engine. So basically, because remember, you need to transfer data, and the data right now probably in memory somewhere, and you want to transfer it to the disk, right, to storage device. So yeah, so that would be also kind of expensive operation because maybe you have to transfer it through this interface, and that takes a lot of time, right? So rather you would say, okay, do the opposite. You can access any memory I have, and you can just transfer data from this address, right? So basically, CPU will not participate in this data transfer. Okay. So what we can do? So the previous approach was like programmed I/O. So we would have to kind of say, we would say, okay, we need to write data, all this stuff, right? So how can we do it here? So you can program the DMA engine by telling where the data lives in memory, right? So and then how much data to copy and which device to send it to and so on. So that's pretty much what you can see. At the point when the OS is done with the transfer, and and then at this point it will be done with the transfer, and then say, okay, I can switch to task 2. I don't care what happens like when this data is getting transferred, when it's getting scheduled, so whatever, right? I'm going to execute task 2 at this moment. So yeah, so when DMA is complete, the DMA controller raises an interrupt, right? And the OS knows now that this transfer is complete. Again, that will not be worthwhile if I just want to transfer 4 bytes. But if I'm transferring megabytes, that can be really worthwhile, right? So in the past, in older system, we would have like a single DMA engine. In modern systems, we have per device DMA. Yeah, so by the way, the interrupts and DMA, even though like you can see that in personal computer, that was kind of also, I think, uh, some incremental progress, but those were already known back in 50s, right? So it's not like it's a completely new concept. So now one question that is there any issue with this DMA? Any idea? So what kind of problems can we have with DMA? So as I said previously, the device can access pretty much any memory that you have, because it can have basically access to entire physical RAM. And that's pretty bad. Maybe you will connect some, chip, there is some, I don't know, some cheap flash drive, or, it will, or maybe not flash drive probably not a good analogy, but maybe you will connect some uh, USB, maybe not like not maybe USB, but there is also Thunderbolt, right? So I mean it's Thunderbolt or USB for whatever it is. Now that's kind of combined also the standards, right? So but basically in Thunderbolt you would also have this access, direct access. You would have DMA and all this stuff. Let's imagine I can connect this device there, and that maybe has a NIC. Maybe it will access my entire physical RAM and transfers this data to some, some remote server in some different country, right? That would be pretty bad, right? And I don't have no idea even, right? So because I'm just connecting my network adapter, I don't think that it's doing anything bad, but it's just basically transfer all my data from all my RAM to somewhere else, right? So that can be a malicious device pretty much, right? Not just malicious program, someone can build a malicious device potentially, right? So, and that is a problem, especially if there is something that is this device is connected to internet or something like that. Um, so who knows what may happen, right? So, and therefore, it's really bad to give access to all data. So sometimes um, you pretty much want to do translation similar to what we do with page tables. So we want to translate virtual address to a physical address. So, but this process only has access to its own subset of memory, right? Doesn't have access to the entire memory. So something similar you want to do with IO devices. So you want to create special IO virtual address. Don't confuse it with virtual address, IO virtual address. And that should be translated to a physical address. So like for virtual address translation and virtual to physical, we have MMU. Remember, that's called MMU, Memory Management Unit. So that's typically nowadays part of the CPU itself, right? And but that's what is doing the translation. So similar thing that we have for IO addresses. So we will translate that through IMMU. So that's pretty much a similar idea. So why is it also useful? I mean, aside from isolation, well, pretty much for the same reason, like we have IMMU, right? Also regular MMU, right? So sometimes, the virtual address has to be contiguous, but physically, maybe RAM, I cannot find contiguous chunk of RAM. So because I have this translation, I mean, I have a contiguous chunk of virtual memory, which corresponds to non-contiguous chunk of physical RAM. So that helps with this fragmentation or whatever it is, right? So we can still use memory more efficiently, because otherwise I may say I need 1 GB of physical RAM, which is contiguous. And who knows, maybe after I run my system, I want to be able to find it. So that's really a good idea to have that translation as well. Of course, it's not free, but it's something that we can also use. So nowadays, I think most modern computers have IMMU. So in the past, it was something that was optionally available on maybe high-end systems, but I think even my laptop has IMMU nowadays, right? So that should not be a big deal. Maybe some smaller systems like tablets, they don't have, of course, that. But yeah, that's pretty much what we can do. Any questions so far? Yeah, so just know the two main concepts, right? Interrupts and DMA. So both of them are needed to offload CPU, because CPU time is ideally should be used for something more important, right? And we shouldn't be. And anyway, that impacts user experience, even if it's not doing anything important. As I gave you an example, is the floppy drive that would basically paralyze your entire system, and you cannot do anything while it's doing this disk formatting, right? So you don't want to do that. So yeah, that kind of makes user experience pretty bad. Okay. So one thing I will also wanted to clarify, right? So yeah, that's just just to kind of reiterate PIR versus DMA, right? So PIR sometimes it's also called program I. You will see that abbreviation that you know, in the past I think hard disk would use PIR or something like that. That's pretty bad, right? That would make your system slow. But you know, then later they transitioned to DMA and so on, right? So that would, I mean, of course, that was a long time ago, right? So, but again, this is just the abbreviation that you will see. For Pi, it's basically relies on polling. So now you will sometimes hear another term called port IO. Not PI, that don't confuse it with PIO, right? So port mapped IO, right? So to be more precise, PMIO, right? So that's a different term. So let's talk about this one. So what is PMIO and MMIO, right? So memory mapped IO. So basically, there are two ways to access registers. So I said that we need to somehow access registers. So one way to access this register is to use a special instruction like in or out in x86. That's basically, you know, if you want to read something, you use in, outside, like you want to write, you would use out instruction. That is kind of legacy. It's considered now legacy, right? But in the past, that was kind of a separate IO address space, so to say. You had memory address space, but you also have a separate IO address space. So you would say this IO port number, you write to this, that's pretty much like IO address, or you write to this another IO address and so on. And then registers will be mapped to this corresponding ports. So this is why it's called port mapped IO. So that's basically having a parallel system, like in addition to memory, you have another system for IO, and you have special instructions in CPU to deal with this. So yeah, again, this will still be used for legacy device. I guess if you're using floppy drive, that's still, I guess, pretty much what you're gonna use in and out instruction. Yeah, so but you know, in and out is actually a little bit trickier. They can be they are privileged, they are normally privileged instructions, but you can enable certain ports in user space. So there is a possibility to kind of create a port bitmap and say this user space program can access certain ports. So similar to what we have with page tables. But you know, this is very limited, and I would say because it's legacy, it doesn't really work that well. And you know, normally nowadays no one is using this feature. So normally you would kind of assume that in and out, even though they're not fully privileged instructions, you can potentially use them in user mode. Typically, you only use them as privileged instruction and don't enable anything in user mode. So now with memory mapped IO, it's you know, it's different, right? So we just say we don't need this separate address space, the ports, just use memory addresses, and then I will just use a regular memory load and store operation to access these registers. So I mean, what's the point of using some special instructions when I can just use regular memory? Yeah, so basically, yeah, that's the idea. So hardware makes these device registers are visible as like regular memory locations. So it's very similar to frame buffer, which we had in project 2. So of course different because frame buffer is still some sort of special type of RAM, but this is the register device register, but it's the same idea. So you will also find that some memory address ranges are reserved for registers, like typically in some upper ranges, right, after 3 GB. So, the textbook actually may say that PMI is preferred, right? So, but actually, I would say but the textbook is for 32-bit processor, and nowadays we're dealing with 64-bit processors, and memory mapped IO is more preferred, right? So nowadays, right? So, and one example is that 64-bit operations are only supported in MMI. So, for example, you cannot in and out instruction, you can only access up to 32-bit registers, right? So, if you need to access the entire 64-bit register, that's only available from MMI. You don't have a way to write entire 64-bit. I mean, you can still probably write two separate instruction, to split the 64-bit and the 232-bit portions, but it's not a single instruction. So also one thing to mention, sometimes we want to build systems such as microkernels, where we have pretty much all device drivers running in separate user processes to provide better isolation. So we move them from kernel to user space. And at that point, what we will need we will need to have access to device registers. But how can we get the device registers if we use like in and out instruction? As I said, it's possible to control it, but it's not that great. So, but with MMI, you already get this because you can just use page tables. So you just need to map the corresponding page which contains this device registers, assuming that this device uses at least page level granularity to map these registers. You shouldn't have any issues, right? I mean, of course, if two devices occupy the same page, that's going to be a problem, right? So, but if at least for two devices, you have, typically, I think they should be putting that in different pages. So that way you can map it to this process, and maybe in another device you can map to another process, and so on. So you can potentially access devices from user space as well, because it's a regular load and store instructions, and you can map them to memory. Any questions? Okay. Yeah, let's go back to the virtual file system. So we're pretty much done with IO devices, like in terms of how IO works and so on, right? So we won't go into too much more detail about that in this course. But I guess the remaining part of the course, we will focus on storage and file systems. So that will be like the upper level, right? So the EFS and, whatever is outside of EFS as well. So like IO devices, I hope that you have some general idea now how that works. In case if you need to ever develop a device driver, you at least know where to start, right? So you will not be scared by seeing some memory allocation and you write to some memory allocation that is actually a register, right? So, so now you already know that. Okay. Yeah, so let's talk about virtual file system. Again, just pretty much a general interface which we want to use to access file systems. So we can support multiple file systems at the same time, and because we also want to interact with page cache. So there's different reasons why we want to do that. Sometimes we want to also provide some, we pretty much want to have like identical API as well as page cache, but also one more thing, maybe there is something common across different file systems, like for example, directory traversals can be common across different file systems, that should be also shared so that you don't re-implement that over and over again. So in Linux, you can find this include Linux VFS.h. So this is where pretty much you will find this the VFS layer. I'm talking about the Linux kernel code. So if you download Linux source code, go to include Linux FSH, you will find that pretty much what belongs to the VFS layer in Linux. Okay, so just to again to give a high level idea. So we have applications, system calls, go through VFS like open, close, read, write. VFS may interact with page cache, but eventually VFS is going to reach XT4 or ISO file system, and those file systems can also potentially talk to page cache. That is not shown here, but they can also talk. So let's talk a little bit about different caches, right? So directory entry cache. So I already briefly mentioned directory entry cache and inode cache. So let's look in more detail. What is it? What directory entry cache is? So suppose you open some file, like open home user file text, right? So you basically need to get to that file. And file information is stored in so-called inodes that I already mentioned, right? And there you will skip some metadata, such as creation time, modification time. Well, actually, it depends on the file system. When sometimes creation time, for all of them support creation time. There is sometimes you support access time, but access time is really kind of expensive because every time you access a file, even for reading, you have to modify this timestamp. Yeah, so yeah, you have this kind of different timestamps. Also, you have permissions. When you do change mode, you will say, okay, can be accessed by user, this can access by group, and this can be accessed by everyone else. So these permissions are also stored inside inode. What else? Well, it also has to, of course, has some sort of list of data blocks. So it has to say where this file is actually stored. So it says like where this file data is stored. At file offset 0, we have first block, right? So where is it stored in the disk? Like file offset 1, like block 1 and so on, right? So where is it stored? So you have to map it. So you effectively have to map file location to the disk location, pretty much, right? So it's kind of analogous to having a page table where we map virtual address space to a physical address space. It's not exactly the same, but very similar idea. So it's basically each file has its own kind of its own unique version of what was this block is and this block is. So it's basically has its own virtual, so to say, addresses. We don't call them virtual addresses, we call them file offsets or whatever it is, but fundamentally it's a virtual address. So each inode also has an address. So it can be just a disk block a number, but in some file systems such as XT4, XT3, you maybe kind of split one disk block and store multiple inodes inside this disk block. Because maybe inode is like 256 bytes and your disk block is 4 kilobyte. So you can store multiple inodes inside this disk block. So it can be different in different file systems, but there is one way or the other you can always create this unique number. Because certainly it can be identified by disk block and maybe by something else also. Like maybe offset within the disk block. In case of XT, they have a separate map, right? So they will just have only certain number of inodes that you can all create. And the inodes will have their own IDs. So what do we need to do? We need to translate home user file text, this path to the inode address. So we need to like roughly get this like disk block where I can retrieve this metadata. So how can I do that? Well, I need to traverse all this directory. So I need to traverse slash, which is a root directory, right? So remember that the first slash is just the root directory. Then root directory contains everything else, right? So then I go to the home directory. Then I find in the home directory, so in the root directory, I find the home directory. In the home directory, I find user directory. In user directory, I find file text file. And after this, I'm done, right? So that requires multiple steps. So typically the way that it's done in file systems, that at each step, like when you traverse a directory, you can, for simplicity, again, it's not how it's implemented in real file systems, but for simplicity, you can view a directory as a special file which contains a list of about like a list information about other files. So it will say, okay, home has user entry, and that is the address for like inode now address. Then it has maybe a user2 directory, and that's another inode number, right? Maybe user3 directory and has another inode address. So it's pretty much a list of entries and their corresponding inode addresses. So now the question is how you store it. Sometimes you have cache tables, sometimes you have balance trees, like what kind of what kind of structure you use for directory. It's a different question. Every file system will do it differently. I mean, in the worst case scenario, you can just have like just like a list pretty much, right? So which doesn't have to be even sorted. But then search time will increase because you can, if your directory becomes pretty large, you may need to read a lot of data blocks to retrieve this to find this translation, right? Maybe you have to go to one like you check one entry, it doesn't match another entry. You have to read more and more data from disk to find that translation path. So again, this depends on the file system, but just view it as some sort of special file which contains information where another file is stored, right? So it has an entry name and the corresponding address. So why do we need directory entry cache? Well, maybe at some point I'm gonna access home slash home one text. Even though that's not home user file text, I still at least may I still may need to cache the root directory slash, and I still need to cache home, right? So I still need to cache those. So at least I don't need to traverse them. I mean, in home, maybe I'll have to find one text, but that's a different story, right? So I may need to traverse directories, and even if the path partially matches to what I already have in the cache, it still can be useful. So inode cache. So again, at each point, we have to go to different inodes. So therefore, it's natural to have this inodes in memory also, right? So because I'm going to be accessing this inodes over and over again, and not to mention that if I'm going to open file text over and over again, maybe it has some important information for the program, and the program has to read it over and over again. Maybe it's some settings files, I don't know, right? At that point, I also probably want to keep it in memory because I don't want to go back and to the disk, read it, and that's like, remember, to read something from disk is very expensive. You have to issue a command, it has to, then you have to get an interrupt, right? So you have to program DMA engine, you have to get an interrupt, a lot of steps, right, before you read something from disk. It's much faster to access something from memory. So, okay. Yeah, so let me also briefly talk in the remaining part of the lecture today about file system consistency. So historically, file systems were not safe in the event of failures. Like if you look at some legacy file systems such as FAT or FAT32, they could pretty much lose your data, right? So if you like lose power, you reboot the system, that would be kind of pretty much dangerous to your files. You may really lose some important files, and moreover, not just files can be lost, but your entire file system can get corrupted, right? So maybe you will lose, maybe you write into some directory, and maybe you're writing something to the root directory. Imagine this failure happens while you're writing to the root directory, and you were changing the block or maybe some data inside the root directory, and maybe root directory is not pretty large. It just has information about other inodes, and now this data is corrupted. You don't know where your files are, right? So all your files are gone, right? Because the moment your root directory is corrupted, you cannot reach any other files. So that can be an example of a catastrophic failure, right? I mean, you may still be able to recover it. Maybe you can run some file system checker, which will find, okay, there is this inode. For some reason, it's not used anywhere, like an orphan file or something like this, right? So at least you can get these files and and recover that from that catastrophic failure. But it's not really something that will be guaranteed. And it certainly will spend a lot of time scanning the entire disk, and you have to use special tools for that and so on, right? So this is pretty bad for file system recovery. So what can you do? You can use, I guess there are three main mechanisms that can be used. So one mechanism is known as soft updates. So in BSD, like fast file system or UFS, so they would kind of order each operation such that you can always recover, right? So they will have to kind of do something in a specific order. But this is not very generic scheme. It's kind of specialized to this particular file system, and I'm not sure how well that is, right? So like how well it works, right? So it's still maybe having some edge cases which are not, where you cannot fully recover. You can order some operations, and by ordering it, you can prevent these catastrophic failures. But another possibility is that use journaling. So have you heard about journaling? So the idea of journaling, the fundamental idea of journaling is that there's different kind of journal. Sometimes you want to journal both metadata and data, right? But losing data may or may not be acceptable, right? So for example, if I lose some file, that may not be a big deal, right? Maybe I was typing something like in last half an hour in some document, and I lost that file. Yeah, I will be also disappointed, but probably not so much, right? I'll just do that work again, right? So losing data is sometimes acceptable, but losing metadata is typically never acceptable, because the moment you lose metadata, you lose the file system structure, right? So maybe you're losing inode, like you're corrupting inode for the root directory, and you lose everything. And even if it's not a root directory, maybe it's my documents directory, right? I'll lose all my documents, right? So that's still pretty bad. So it's much worse than losing data sometimes. So metadata is something that is really important. So typically you always want to preserve metadata. So data you may want to preserve, that depends, right? So again, journaling can be both for metadata and data, but at least it's typically for metadata. And for data, they may use some other techniques, like such as, for example, ordered writes, like XT4 has this option where it would order some writes and make sure that data is updated before metadata is updated. So that way you can preserve these failures. But the idea is in journal at least gonna work with metadata. So what does it do with metadata? Let me kind of talk briefly, because we won't have too much time to go into too much detail about journaling. But the main idea that you have a special area in your disk. Let me actually review and draw that. So the main ideas that you have, let's say it's your disk. And this is where you store your inode, maybe another inode, some block number, right? So before writing to this location, you will write to a special designated area called log area. A journal, like log area, it's typically called on disk log area. So the idea is that before modifying this actual location, you will start a transaction. So transactions, start transaction. Start transaction, right? So you'll start transaction. You will basically duplicate this inode here in this buffer. If you need, during this transaction, you need to modify another inode. Maybe you are creating a new file, right? So you are initializing a new inode because it's a new file. And you're also modifying the parent directory. So that's modifying another inode. So you will at least need 2 inodes to be modified for that operation. So the idea here is that you will do these modifications. You will either do these modifications or will not do them at all, right? So it's totally fine for journaling to lose some last operation, or maybe even several last operations that you had if you lose power. But what you want to you basically want to go back to the previous good state, right? So when this file was not created. So in other words, you reboot your system, this file doesn't exist. But it's fine, right? It's still going to be acceptable. You don't want to end up in a situation where file is kind of partial exists, right? So you either want to make sure that the file exists or it doesn't exist. So we want to make sure either operation is completely done or not done at all. So and each operation may have multiple modifications. So I need to modify multiple inodes, right? So I want to do that atomically in one transaction. So you already know the word atomic, right? So I want to do that indivisibly in one transaction. So pretty much, let's say if I want to modify 2 inodes, I want to write this transaction, right? So I will write this transaction here, duplicate this inode, and only after I'm done, I will modify the actual locations here. So that way, if let's say failure happens before I finished writing this transaction, right? I can discard it. So I can just discard it because no damage has been made. I haven't written to the actual location and that transaction is incomplete. I can just discard it. If this transaction is completely written, then I will just replay it. And when I replay the transaction, I will replace this inodes from this area to this area. So I will just copy it from this area to this area. So let me talk a little bit more next lecture about this.